Today we're going to look at matrices and systems of equations and move forward how those are tied together. We want to explore some techniques for solving systems of equations using matrices. You might remember that a matrix is a rectangular array of real numbers. Every item listed in a matrix is called an element, and an element is identified by its position in the matrix. For example, if we say A sub 21 is an entry, that means that we're in the second row, the first column. And a matrix having m rows and n columns is said to be of order m by n. So let me just create one here with the elements. A sub 11, A sub 12 means we're in the first row, the first column, the first row, the second column, and so on and so forth. So if I called this matrix matrix A, then I could say matrix A is a 3-row by 2 column. So this is a 3 by 2 matrix. This is my M and this is my N. So let's give that a little practice. I want to determine the order of the matrix. This matrix has 2 rows and 2 columns. This is a 2 by 2 matrix. Matrix B is 2 rows and 3 columns, and matrix C is 3 rows and 2 columns. When you write an augmented matrix, we're going to be given a system of equations, and we're going to look at just the constant terms or the coefficients and leave out the variables. So the coefficient matrix is just the numbers, the constants 1, 1, 1. So in the first row we would have 3 ones, and then 1, negative 2, 1, that would be our second row, and negative 1, positive 1, negative 3 in the third row. These are the coefficients of the matrix. And in each column, this is the x variables, this is the y variables, and this is the z variables that correspond to those constant terms. And when we're asked to write an augmented matrix, that's when we leave, a lot of times it'll be 3 dotted lines. Some people prefer to put a bar there to separate the coefficient matrix from the solution terms on the right-hand side. Either way, this would be called the augmented matrix. So it takes into account every constant term in the equation all the way across. So let's give that a try. So we want to be sure that we align the variables up together. And anywhere there's a missing variable or a missing term, we're going to put a 0 for a placeholder. So we have x and y and z, and that's equal to negative 1. So this is my block between the equation part and the equal part. In the second row, we have no x, 1 y, negative 2 on z, and that's equal to 0. And in the third row, we have 1x, no y, and 3 z's, and that's equal to positive 1. So this is called our augmented matrix. Now, in our last lesson, we looked at elementary row operations. So I'm just reminding you here what it means to be in echelon form. That's when we have that stair-step pattern with the matrix, and you can perform those elementary row operations by interchanging the position of 2 equations, multiplying one of the equations by some non-zero constant, and adding a multiple of one of the equations to another equation. And we can interchange those operations around. So looking at this first one, we want to give this original matrix and perform the row operations that they're suggesting. So if we take row 1 minus row 2 and call that our new row 1, this is going to become our new row 1, then row 1 minus row 2 is 1 minus 0, that's 1. and 1 minus 1, and 3 minus negative 2, and negative 1 minus 0. So that's my new row 1. The other two rows, we're going to leave those alone. Then the next row operation we want to do is we want to create a new row 3. So our new row 3 is row 1 minus row 3. So we got 1 minus 1, that's 0. So in other words, we're not changing row 1, we're not changing row 2, but we're going to get a new row 3 here by doing row 1 minus row 3. So 1 minus 1 is 0. 0 minus 0 is 0. 5 minus 3 is 2. And negative 1 minus 1 is negative 2. So you can see our goal is to get all the zeros that we can to make that reduced row echelon form. Now, because row 3 also has a factor of 2, if I divide each term in that row by 2, I'm going to get a reduced row 3, and that would look like 2 divided by 2 would give me a 1, and negative 2 divided by 2 would give us a negative 1. So again, I'm simplifying that down as much as possible. Then to get a new row 1, I want to go back and look at row 1, and I want 5 times row 3, and that's going to give me a new row 1. So if you think about 5 times this, when we add those together or subtract those, it's going to make a 0. So my new row 1 is going to be 1 minus 5 times 0, and 0 minus 0, and 5 times 5, but 5 minus 5 is 0, and then negative 1 minus 5 minus negative 5, so adding 5 is going to give us a 4 there. And then this row stays the same, and the third row stays the same. Whoop, not a negative. 1, whoop, lost my pen. 1 and negative 1. Okay, then finally, we're going to get a new row 2, by taking the row 2 we have and multiplying 2 times row 3. So row 1 is going to remain 1, 0, 0, 4, and row 3 is going to remain 1 and negative 1 in the last 2 columns, and then row 2 plus 2 times row 3 is going to give us a 0 here and a 1 here, and 2 here and negative 2 here is going to give us a 0, and 0 and 2 here is going to give us a negative 2. Now, here's the interesting part. If I kind of divide that up, you see over here I have a diagonal of 1s, and all the lower elements and all of the upper elements in this triangle are all zeros. This is called the identity matrix. And the great thing about the identity matrix is this gives me the solution for my x, y, and z. Because the first row says x is 4, y is negative 2, and z is negative 1. And I believe we see that in x is 4, and y is negative 2, and z is negative 1. And that's how what we call reduced row echelon form. If every column that has a leading 1 has zeros in every other position above it and below it. And that's what we saw in that last example. We had a leading 1, and everything below it, or everything above it and below it, or everything above it was all zeros. Then that was called reduced row echelon form. And this is my solution set here. So my ordered pairs where the system intersects, those are my solutions, that ordered triple there. So let's look ahead to a little more complicated. This one we're going to work on our own. Oh, well, that was example 3, wasn't it? So there's our solution, 2, -3, 4. So-called Gauss-Jordan elimination with matrix operation. So we've already got our augmented matrix here to match this system. And I think I want to take row 1 minus row 2 and get a new row 2. So let's say row 1 minus row 2 is going to give me a new row 2. So we'll keep row 1. And 1 minus 1 is 0. 1 minus -2 is 3. 1 minus 1 is 0. And 3 minus 12 is -9. I can also do another thing at the same time. Let's say we take row 2 minus row 3 and get a new row 3. So we'll also do that. So row 2 minus row 3 could give me a new row 3. So 1 minus 1 is 0. -2. Now I'm going to say row 2 plus row 3. -2 plus 1 is -1. And 1 minus 3 is -2. And let's see, let's do it this way. 12 minus 17 is -5. Double check that, make sure I did that right. So I'm really adding row 2 and row 3. So this is my new augmented matrix. And remember, our goal is to get zeros here and a 0 here and a 1 here and a 1 here. So let's say in this one we take row 1 plus row 3 and get a new row 1. So row 1 plus row 3 is 1. Row 1 plus row 3 is 0. Row 1 plus row 3 is -1. And row 1 plus row 3 is -2. I'm going to keep row 3 just like it is. 0, -1, -2, -5. And I see this 3 and this 9. Let's divide that row by 3 and get a new row 2. So we'll have a 0 and a 1 and a 0 and a -3. So it looks like y is -3. Now you could stop there and go and do back substitution, but just to stay with the theme of Gauss-Jordan elimination, I'm going to continue to work and keep row 1. So we have 1, 0, -1, -2. And we're going to keep row 2 since we already found a y value. And then row 3, I'm going to get row 3 by adding row 2 and row 3. Because if we add these together, we'll get a 0 there. So I've got a 0 and a 0 and a -2 and a -8. And you see these both have factors of 2. So this gave me a new row 3. So I could divide that by -2 on row 3, and that would give me a new row 3. So we would have 0, 0, 1, 4. So I know Z is 4, and we know Y is -3, and we're looking for row 1. So what can we do to row 1? We could take row 1 plus row 3. So if we left this row 1 here and we added that, we'd get a 1 and a 0 and a 0 and a 2. Hey, and then we'd have it, right? So I should leave that alone and we'll come do that again here. So row 1 plus row 3 is going to give us a new row 1, and we'll have 1, 0, 0, 2, 0, 1, 0, -3, and 0, 0, 1, 4. So there's our augmented matrix. It's now in reduced row echelon form, where x is 2, y is -3, and z is +4. So our solution to the system is 2, -3, 4. Now, to save time, I'm not going to go back and plug it in. I'll leave that step to you to make sure that works. So this one we want to solve with, this one is going to have infinite solutions, and our system would look like 3 for x, 7 for y, there's no z, and 1. And then 2x, wait, these are all divisible by 2, so let's divide the entire thing by 2. So 2x divided by 2, and 4y divided by 2, and 2z divided by 2, and 0 divided by 2. So we have this augmented matrix to start off with. And if we take row 1 minus 3 times row 2, that'll give us a new row 1. So row 1, and we're going to multiply this by -3. So that's going to give us a 0, and 7 minus 6 will give us 1, and 0 plus 3 will give us 3, and this times this will give us 1. Keeping that second row the same. In this step, we'll take row 2 and multiply 2 times row 1 and subtract it, and that'll give us a new row 1. So I've got 2 times this, 0 minus 2, let's see, row 2. So that's going to, no, I'm sorry, 2 times row 1, 2 times 0, and 1. So 1 minus 0 is 1. 2 minus 2 is 0. -1 minus 6 is -7. And 0 minus 2 is -2. And then what else can we do? Let's see. Let's put, we want a 0 down here. So we'll put row 1 is going to go to row 2. We're going to interchange row 1 and row 2. So this became the new row 1, and row 1 became row 2. So all we did is move that down there. Now what are we going to do? Well, we see we can't really get this to be a 0, so we have x minus 7z equals -2, and y plus 3z equals 1. So we're back to that infinite solution where we had 3 equations. We had 2 equations, but we had 3 unknowns. So all we can do now is let our z variable be any number. I'm using b in this unit, so b is any real number. And no matter what number you pick for your z variable, then x can be 7b minus 2, and y would be 1 minus 3b. So we have infinite solutions where our z variable is any letter, any number in the real numbers. So x is 7b minus 2, y is 1 minus 3b, and z is any real number, where b belongs to the real numbers, to the, not integers, to the, I said real numbers and I wrote a z, where b is an element of the real numbers. And then we should try one with no solution to see what that looks like. And in an upcoming lesson, we'll also do this with the calculator, which will speed things up. So we got 1, 1, 3. On Y's 2, 1, negative 2. And on Z, 0, 4, and 6. So taking this augmented matrix, I'm going to leave row 1 alone. And I'm going to take row 2 and subtract row 1 to give me a new row 2. And we'll take row 3 and row 1 and give us a new row 3. Okay, so row 2 minus row 1 would be 0, negative 1, 4. And row 3 plus row 1 is going to make 4, 0, 6. But let's cut that in half. Let's take half of that. So half of 4 would be 2, and half of 6 would be 3. Okay. Next, we're going to take row 1 and subtract 2 times row 2. So row 1 and 2 times this is going to give us a 1. And row 1 minus 2 plus 2 is going to give us a 0. And this minus 2 is going to give us an 8. And leaving row 2 alone, we have that. I said subtract. I meant add. 2 minus 2 is 0. And 2 times 4 is 8. So 0 plus 8 is 8. Okay, and we're leaving that column alone. The rest of the rows alone. But let's switch this. If we took negative 1 times row 2, we could have the answer for Y. So that would be a positive, and this would be a negative. And then we want to get some zeros down here, right? Or a 0 here and a 1 here. Okay, in the next section, we're going to leave row 1 alone, and we're going to leave row 2 alone, and we want to do row 3 minus 2 times row 1. So row 3 is 2 minus 2. That's going to give us 0. And 0 minus 0 is going to give us 0. But 3 minus 16 is going to give us negative 13. And then if we divide row 3 by negative 13, we would have 1, 0, 8, 0, 1, negative 4, and 0, 0, 1. So you can see, let's see if we did row 1 minus 8 times row 3, we would get a 1 and a 0, and then 8 minus 8 would make this become a 0 here. You follow me on that? So I could get a 0 there. And you can see I don't have any solution. One more step here. This would give us a new row 1. And if we divided, let's see, how can I do this? Row 2 plus 4 times row 3 would give us a 0 here and a 0, a 1 here, and 4 plus this would give us a 0 here. And you can see all I ended up with is the identity matrix. And when we get down to the identity matrix, then we have no solution. Now, I don't know about you. We did them. I practiced them to show you what it looks like. But in reality, probably using back substitution would be quicker. Then just to practice this one more time, using curve fitting or point fitting, if you want to call it that. This one is a little more complicated. It's a cubic polynomial. I'm going to request that you turn off the video and set up your own system and then come back to see if yours matches mine. Okay, after substituting, this is my system that I have. And if we write some numbers, equation 1, 2, 3, 4, this is the equations we got from substituting our ordered pairs into that. So if I do, let's take equation 2 minus equation 1. And that'll give us 7a minus 3b plus c equals 7. And if we take equation 2 minus equation 3, that'll give us a plus c is negative 5. And then equation 4 minus equation 3 would give us 13a plus 4b plus c equals negative 1. And then I need a fourth equation, so I'm going to keep equation 3 for my fourth equation. A plus b plus c plus d equals 1. So we eliminated all of the d's except for that first one. This is my new system. Now let's take the new equation 3, 13a and 4b and c, and subtract negative 7a plus 3b minus c minus 7. So we're going to subtract equation 1. That'll give us 6a plus 7b equals negative 8. Now we want to get rid of another c term, so we could take 7a minus 3b plus c equals 7 and subtract a minus c and positive 5. So equation 2. This will produce 6a minus 3b equals 12. So if we call this equation 5 and this equation 6, we can put those together. 6a plus 7b equals negative 8, and then subtract 6a, add 3b, and subtract 12, and we'll have a term for b. So it looks like b is negative 2. And then we can back substitute here. So 6a, actually we could divide by 3. So 6 divided by 3 is 2a, and 3 divided by 3 is 1, and 12 divided by 3 is 4. So 2a is 2, and a is 1. And then go back to the a plus c equals 5, or a plus c equals negative 5, I'm sorry. And we had a is 1, so c is negative 6. And then we have the last one, a plus b plus c plus d is 1. So if a is 1 and b is negative 2 and c is 6, and we're looking for d, then d is 8. And we have the 4 coefficients, which is the solution to our system, but we're trying to write the cubic polynomial in that form. Y equals 1x cubed So ax cubed minus bx squared minus 6x plus d. That's 8. So a is 1, b is -2, c is -6, and d is 8. And that's the end to lesson 3.